this video, we'll find out how water helps us understand light. In your physics journey so far, you would have covered vector addition. But in this next video, because we will need vector addition, I'll cover it again. So, if I have two vectors, and they're both pointing in the same direction, one vector is slightly bigger than the other. If I want to add them together, we'll go head to tail, and then going head to tail, we take the resultant vector of those two in addition. So the resultant vector of those two is going to be a vector the size of this one add this one. Because they're both pointing in the exact same direction, we're just adding together the magnitudes, and the resultant direction is going to be the same. If we have one vector pointing up and one vector pointing down, and we add these two vectors together, what do we get? So, from this, we'll see that the resultant vector, if we put them end on tail on end and so on and so forth, we're going to get a vector which is going to be smaller than the two vectors. So it's going to be the difference between these two vectors. So this is vector addition when we have a vector pointing in one direction and one pointing 180 degrees in the opposite direction. Ultimately is subtraction. So this is important to know when we talk about the interference with waves, because we can have constructive and deconstructive interference. If I have two electromagnetic waves here, so remember electromagnetic waves have an electric field and a magnetic field. The magnetic field is 90 degrees away from the electric field. So, if I have a wave here, and I have a wave here. So these two waves are going to be in phase. So these two waves are also going to be coherent. Just makes life easier for us. So, if I draw in the vectors for both of these waves to represent the electric field, what do you think would happen if we then had both of these waves acting together at the same time? We would actually get interference between the two waves because they're both the same type of wave. We get vector addition. So we add up the electric field vectors on one of them and the other one, and the resultant wave is going to be the addition of the two of them. So my example here, because these are in phase, it's going to be constructive interference. Constructive interference is where we have two waves acting together to produce a bigger amplitude. So amplitude is the height of the wave. So constructive interference, the two waves work together to create a larger amplitude. They exaggerate the size of the wave. Deconstructive interference would happen if one of these waves is slightly out of phase. So if I had this bottom wave 180 degrees out of phase, so wherever we have a crest on this one, we'd have a trough on this bottom one. If I draw in the vectors for these, and then add them two together, we'll see that the addition of this one and this one leads to annulment. We have complete deconstructive interference of the waves. So, from these two waves, we can see that deconstructive interference happens when our two waves are out of phase. Depending on how much out of phase would depend on how much deconstructive interference we get. But deconstructive interference leads to the reduction of the amplitude of the waves and can also lead to complete annulment of waves. Consider two waves. These two waves are coming from a monochromatic light sources. So these two monochromatic light sources are producing these two waves, wave 1 and wave 2. So If the light source is monochromatic, these two waves are in phase. They're the same frequency. So if they're leaving in phase with the same frequency from point A to reach point B, when these waves travel in a straight line to get to point B, because they travel the same distance, they're still going to be in phase. What happens if instead of point B, I now have a point P? So we can see point P is a straight line from wave number 1, but point P is on a diagonal from wave number 2. That means that wave number 2 has to travel further than wave number 1. When this happens, our second wave may or may not be in phase still, because it has to travel further. There's a trick to this. If the distance that wave number 2 has to travel is exactly one wavelength or a number of certain wavelengths away, but it has to be exact number, so one integer number away in wavelength terms, these two waves are still going to be in phase. So if I have, let's call my integers m, and my wavelength lambda. So if my distance travelled is going to be m lambda wavelengths away, so this wave here has to travel m wavelengths further than this top wave, they're still going to be in phase when they reach point P. However, if our second wave, the distance from the second wave starting point to our point P is m plus a half lambda wavelengths away, so it's exactly half a wavelength, say further or back, or a number of integers of half a wavelength, we're going to get deconstructive interference, because our two waves are going to arrive at the same point, point P, and they're going to be out of phase. They're going to be half a wavelength out of phase. When they arrived at the same time, they were in phase and they constructively interfered. When they arrived with a m lambda wavelength difference, they still constructively interfere because they're still in phase. If they arrive and they're m plus a half lambda wavelength away, they're going to deconstructively interfere. So, if we have two monochromatic light sources with two waves, they can constructively and deconstructively interfere with each other. This depends on the distance that the second light source has to travel further to get to the same point as this first wave. If it's m lambda wavelengths away, m being just an integer, we're going to get constructive interference. If it's m plus a half wavelengths away, we're going to get deconstructive interference. Alright, so let's look at this on a slightly different approach. So, if I have one wave source, remember, waves are not just in the one dimension that we're looking at here. They're in 3 dimensions. So basically, they're leaving the source in a sphere-like fashion. But that's a bit hard to try and understand on a book or a page, so we tend to do it in the 1 dimension. But we can also do it in 2 dimensions in a book. So, a 2-dimensional view of a wave gives us something that looks like you threw a pebble into water. So if I get this up, what I've got here is a wave generator. This is the homemade wave generator that I made using an overhead projector, a container, some water, and a pin to cause the ripple. So we can see when the ripple was caused, we get the wave leaving the source in a circular fashion away. If we have now 2 pins causing 2 waves, we can see the interference between the 2 waves. We can get some bright spots, we can get some dark spots. So these are points where the wavelength of these 2 waves is going to be either m lambda wavelengths away, so we get the bright spots, or m plus a half wavelength away, where we get the dark spots. So we can draw this up into a geometrical fashion. So we can draw this up and we get a diagram that looks something like this. So you can see the points where our amplitudes are going to be increased due to constructive interference, and points where our amplitude is going to be decreased or annulled possibly due to deconstructive interference. So at each of these points we're going to have the wavelength of the travelled differences of the two waves at either m lambda wavelengths or m plus a half lambda wavelengths. So the key points from the video today. If we have two waves that are in phase, they can interfere with one another. They can either do this constructively or deconstructively. Constructive interference is where we have the two waves in phase of each other and the vectors of their electric and magnetic fields are getting added onto. So we get larger amplitudes in constructive interference. So the crests and the troughs are at the same point, so they're in phase, and we get these getting bigger. Deconstructive interference is where we have the two waves out of phase. If they are half a wavelength out of phase, we get complete annulment of the waves. That means that if we have a crest on one of the waves and we have a trough on another one, when they add up together in the vector sums of the electric and magnetic fields, we get zero. So they annul each other. We can have deconstructive interference where it doesn't completely annul, it just manipulates the final wave, but in general terms we normally talk about complete annulment and complete addition on top. So constructive and deconstructive interference. Also, if I have two waves and they're travelling to some point, if our point is m lambda wavelengths away from our second wave, we're going to have constructive interference because the two waves are going to arrive at this point in phase. If our point P is away from our second wave at m plus a half wavelength away, we're going to get deconstructive interference. This is because our waves are going to arrive at the same point and they're going to be half a wavelength out of phase.